Welcome to modeling discharges from human ESD up to high voltages using multiphysics simulation methods, an EMA Expo 2025 event. My name is Aaron Ward, and I'll be your host for today's presentation. Please be advised that to submit any questions you have during today's webinar, please use the Teams Q&A feature. After the presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar, we will address them over email individually. Our speaker today is Kevin Miranda. Kevin Miranda is the lead product manager of EMC Plus and Charge Plus. Kevin is also Principal Scientist 1 at EMA with a PhD in atmospheric electricity and computational physics. Kevin also has expertise in elementary particle physics and plasma physics. Through webinars or at conferences, Kevin gives regular updates on the development progress of the two software solutions. He is very excited to discuss this update on the latest big development to the EMA physics solvers. Today, Kevin will present work created in partnership with Jennifer, an EMA expert in ESD simulation and testing. We will demonstrate the setup of Air ESD simulation to a handheld device, a cell phone, with internal components. We will also discuss visualization of secondary arcing inside the device and various mitigation methods. Finally, we will demonstrate an integration with Nexxim to help facilitate ESD mitigation using diodes. Without further delay, I give you Kevin.
Thanks, Aaron. Hello, everyone. Thank you for attending this session on ESDs of the EMA Expo 2025. There's a lot to show you today. I'm very excited to kind of introduce the capabilities and maybe even clarify how to solve some of these problems in Charge Plus. And then we have, so I will be talking about just ESDs in our FEM solver at first, and then we will go and do a deep dive in how to set up an ESD problem in Air in our FDTD solver. I'll give some details on what these are in a little bit. A lot of the work today was prepped by Jennifer and I, and a lot of the demos that we are showing and workflows that we're demonstrating are building up onto the latest ESD tutorials that we have in the tool. And then some of the demos I may not have actual tutorials for, but I can always share with you the actual model if you want to try it out on your end in your on your desktop. So again, today we'll be focusing on electromagnetic discharges. It can be an electrostatic discharge, but it's also we'll touch base on the on an RF discharge that we can simulate as well in the FEM solver. This is a usual reminder. I think a lot of people here know what we do at EMA, but our two solutions that we develop at EMA are NSYS Charge Plus and NSYS EMC Plus. NSYS EMC Plus is very focused on electromagnetic coupling to cables and also the electromagnetics generated from currents flowing within those cables to make sure that we have an integrated system from the PCB all the way to the cable and the harness to the full platform for the electromagnetic interference and effects that we're interested in. NSYS Charge Plus is our tool focused on multiphysics, and this is where discharges come in, because a discharge is effectively a multiphysics problem by having electrons and ions that we have to track in the medium that we are breaking down. And so there is a lot of ways to solve this problem, and that's why NSYS Charge Plus is our focus here, because it's optimized to handle those type of multiphysics problems. There's a third new tool that's coming out this year. It's called NSYS SDK Shield Plus. It is kind of a bits and pieces of what you have in the bigger tools, but they are streamlined workflows that are integrated with SDK. So it's an SDK add-on that you can have. SDK is NSYS a tool to be able to model mission and ephemeris and trajectories of satellites and understand how these interact with various electromagnetic and radiation environments. And by coupling it to our tools, we're able to provide an enhanced level to assess mission survivability and robustness to these types of radiation environments. And so we've kind of tailored some of our workflows and made them automatic and integrated with STK Shield Plus. All the tools ultimately are in the NSYS Discovery user interface. We always enhance our integration with the user interface and the tools, and you'll see some new capabilities today that are coming out this summer in terms of post-processing that we're very excited to share with you to be able to take things to the next level. In this case here, we're looking at the charge tab. As always, we have access to the Discovery cleaning and preparation tools for the CAD, but also the CAD design tools and generation capabilities that we have there. And then you can prepare them for finite element analysis or FDTD. And then once you're ready to go, you can go to our EMA 3D and charge tabs to get the simulation set up. To kind of set the stage for the rest of the conversation today, I really want to stress that I'm going to use a terminology for some of these sections. So we have the tabs at the top, design, EMA 3D, charge. We have the sections of the tab. So we have the simulation, environment, excitation section, and then we have the buttons. So we're going to be navigating around these tools to show you how to set up these problems, set up some circuit terminations and so on. So to do that, we would go, for example, to the charge tab, go to the excitation section, select the circuit boundary condition, which is available this summer. And then on the left, we're going to have the simulation tree. So the EMA 3D simulation tree, and right above it, we have the structure tree for our geometry, which is your CAD geometry. As of recently, you can actually pop the tree out and visualize them side by side. On the bottom right, we have what we call the visualization arc, where we have the ability to look at some of the results that we push into the visualization tools within Discovery. So we have the contour plot, we have the mesh, we have the cut plane. In the center, we have what we call the stage. If you are not seeing an EMA 3D stage, you can use one of these arrows next to EMA 3D to navigate back and forth to go from the model stage to the EMA 3D stage. And then on the bottom left here, you're going to have the move handle with some of the kind of visualization default settings that are accessible. In all our tools, you have access to the settings and also to this question mark to bring the user manual out of the tool and visualize all the content for each of the buttons in the tools and explanations of the techniques within our tool. A lot of the tutorials are also available, and some of the things that I'm presenting today will be there, but a lot of the things that I'm presenting today are new and will be added later this summer. When you press F1 on the keyboard, you'll get a lot of details on some of the tools and how they're used. We have a lot of new things that are being generated by our developers in the user interface, and our documentation is catching up. So we have a lot of new documentation that's going to be also added in 25R2. So let me go through this. This is going to be setting the stage for some of the sections in this presentation. So I have restructured this a little bit to try compared to some of the slides that you may have seen before to really answer the question of what to use for modeling a discharge event. So we have techniques to understand charging effects. So how does plasma and high energy particles interact with materials to understand the electric fields generated by those processes. But now we also want to focus on understanding the techniques to use to model discharging. And so we have the full wave finite difference time domain, the FDTD, which is a method for full wave electromagnetics. And it is coupled to a nonlinear air chemistry module. So this is, I'm going to give you a lot of details on this today, is really focused on modeling air from 1 atmosphere all the way to 0.01 atmosphere, which is more or less equivalent to 30-kilometer altitude. It was designed to model discharges due to lightning on aircrafts at various altitudes. It's able to model very small ESDs on a PCB. It's able to model high voltage discharges and really get you the proper breakdown voltage for large complex systems. But for air, now if you actually want to model a discharge in something different, like a solid, a liquid, or maybe any type of gases, you have to the time domain FEM method that we have in the tool. This is also full wave or quasi-static for electromagnetics, and that's the heart of the solver. And inside you have a stochastic tree model. This is a discharge modeling solution that relies on a provided dielectric strength for the material, and it's, as we'll see in a little bit, uses more of an empirical approach to modeling the discharge process, but it still allows you to model the partial discharge inception voltage, for example, or even the full continuing current through the system and the proper discharge waveform associated to the system. And then if you don't know the dielectric strength, but you know a lot about the gas itself, like the reactions, ionization, dissociation, things like that, you can start leveraging the PIC, CFD, and Monte Carlo modules that we have. And I'll show you various ways that we've used it to model discharges in nitrogen, in hydrogen, and also you can use them for argon simulation discharges, and a lot of various approaches. So much higher fidelity plasma modeling and high fidelity modeling. Very computationally intensive, but probably the highest, most robust way, highest fidelity and most robust way to solve these problems with the fundamental principles. So let me start with the discharge capabilities in the time domain FEM, and then I'm going to work through some examples of the stochastic tree model and the methods that we use. Then I'm going to go through examples of how to use the PIC in the CFD solution. And then we'll switch over to the time domain FDTD simulation to understand how to set up more robust ESD gun, non-contact ESD gun simulations on complex devices inside the FDTD. So the stochastic tree model, we can use it for basically any medium. What's really interesting here is that we just need to provide the dielectric strength of the system. It leverages the time domain FEM solver. The FEM solver is in the potential formalism. It is solving Poisson's equation for the scalar and vector potential based on the charge densities that are present in the system. You can see here we have a source term that depends on charge densities of any species that are present. It could be charged particles from high energy radiation that's deposited in a dielectric, but it could also be a space charge contribution from any PIC or fluid charged particles that we're tracking in the system. It can also, it accounts for the conductivity of the system and so on to properly solve for the flow of charges inside the tool. So the stochastic tree model, STM, is kind of an empirical approach to modeling avalanche breakdown. So in this image on the right, we have a conductor in red and a ground plane in blue. And we have mesh elements in the system that are depicted in orange for the dielectric. And this dielectric can be a solid, it can be a fluid, because at the time scales that we're simulating here, any thermal effects are not really considered. It's really purely the electromagnetic discharge that we're looking at, just the initialization steps. We're talking like sub-nanosecond time scales. And what we're looking at is that the fields varying inside this dielectric over time. And if at a given node, the dielectric strength is, the fields exceed the dielectric strength of the material, we are going to consider that node as part of the discharge. And we are going to change its conductivity to be the one of the what we call the post-breakdown conductivity of the system. So that at the next time step, this mesh element is now conductive, similar to the electrode or whatever we set up as the material conductivity after breakdown. And the fields are going to be updated and consider this element as a conductive path. So that when we iterate through this process over time at each time step, we are going to be able to propagate this discharge through the system. We add on top of that to be able to assess if we actually have these nodes contribute or not to the discharge process. This allows us to model the treeing behavior of a discharge, or else you would just always have a straight line between two conductors. But when you break down in dielectrics, you actually create a much wider damage than just a straight line when you damage the material. And in this case, the value of doing it this way is that you can combine this with data from test data. So you can assess conductivity of the materials once they're damaged. You can monitor the time and of the discharge and how long things took to understand the time scales that you want to use. And you can tailor it for a very specific system. And it's because of its empirical nature, it allows us to run simulations quickly and efficiently for various designs of the geometry, but have all the material and simulation parameters defined through data, typically in research from papers and things like that. We can also tweak it to do other things like enhance the fields along the surface, as you'll see in a second, to define surface roughness and behaviors that would enhance the discharge problem. And we can also provide conductivity varying properties across the dielectric or dielectric permittivity changes across the system that could be due to temperature changes, things like that. So we can add more complexity to this problem usually very easily. So this is modeling an oil. So this oil has a breakdown strength that is a standard based on the spec sheet of the oil. Over time, impurities are going to come in and that breakdown strength will lower, or some of the conductivity or permittivity will change in the system. And this is a pretty typical test that's done between two electrodes to understand what the breakdown strength is. And so you set the spacing between the two electrodes at a given distance, and this allows us to understand for this dielectric strength what will be the breakdown voltage. And so in our stochastic tree model, we ramp up the potential here, 38,000, 40,000 volts, 42,000 volts, and we start getting those arc nodes, which are the dots and whites that you see here, the mesh elements that contribute to the breakdown process. And then we also change the color here to model the current JZ flowing between the two electrodes. JZ in this case is a current density, so the very high. They would have to scale by the actual size of the mesh elements that are present here, which are on the order of sub-millimeter size, so it would be very small. And so the current flowing through here is dependent on the current injected through the electrodes. And you can see the time scales here, 14 nanoseconds, very quick. And a lot of the oil is damaged here. And so within 14 nanoseconds, you discharge the oil. And obviously, if there is the time scales are much smaller than any thermal effects or pulses generated through the oil. So you don't have a shock waves model here through the oil. We're really worried about the breakdown voltage and the discharge, which is enough to use this model based on the dielectric strength of the system. One other useful tools is to kind of change and add some defects inside insulators. So you can add a void in this case. If you care about looking at, for example, a manufacturing defect that was generated in insulation that was made out of oil or paper, and then you have a section of the system that's just a pocket of oil, or maybe you have some air pocket in your dielectric surrounding wires or cables, or maybe you have some ceramics that are tweaked in some way based on the dielectric or the putting that is applied to your wires or your conductors. This will actually tend to create a pocket of vacuum or air that can break down quicker than the surrounding dielectric material. And in this case, we can set a dielectric strength that is different for a dielectric strength that is different for the void versus the insulator, and then understand which one is going to discharge first, and if you're getting a partial discharge in the void. And if you do, when that changes conductivity, it going to enhance the risk of discharging the insulation inside the rest of the insulation around that void. So we have various ways to look at the partial discharge inception voltage due to these defects, as long as you can mesh them. But sometimes those defects and that some roughness effects on the electrodes or even some dust might be too hard to mesh. And so an empirical approach to solve this problem is to apply a field enhancement factor that is tangential to a surface or even perpendicular to the surface that can help us kind of understand how a surface roughness might actually reduce the chance of breakdown near the surface. And so this is 25R2. We have this surface roughness or field enhancement factor that we can add. And so instead of doing a pure electric field strength that is assessed at each node, we have a tangential and normal vector or enhancement factor that we can apply along the surface. And that can help us also mimic a surface flashover, for example. In a surface flashover system, a problem or even a discharge at the interface between two dielectrics, you're going to have some field enhancements along the surface of the dielectrics that you need to consider when you do the discharge problem. So here's a kind of an example on how to set that up. You actually go into charge in the domain. You set the simulation type to internal charging. This is how we set up the stochastic tree model. And then you have the solid ESD options here. This is really the stochastic tree model option, so the STM. And it's not just for solids. You can use it for any type of discharge problems where you want to use this empirical model. And then you set the intra-breakdown conductivity and the post-breakdown conductivity, which is the conductivity of the material while the discharge happens and also after the discharge has happened. So the material property changes once the discharge occurred. And this conductivity will tell you what the continuing currents in the system are once the system is damaged, for example. So if you do want to understand what that is, you can solve it. In the release of 25R2, there is a new electromagnetic boundary condition, which is the E-field enhancement. And then you can actually create an enhancement factor along a surface of choice, which will then facilitate the discharge process in a given direction. And so here, this is very useful for a flashover simulation. So we have our two electrodes, one on the left, one on the right. So just to go back into this setup here, we have a red electrode where we're ramping up the potential, and then we have a ground on the right, and then in green is our dielectric. So this is, for example, two traces on a PCB, and then you have FR4 on the surface here, maybe with some dust on it or some water that you do for a specific test to understand high voltage creepage concerns on the system. And so with this flashover enhancement, we can actually also mesh very finely along the surface. We have a boundary element mesh or a boundary mesh method that the solver automatically uses to create very thin layers near the surface. And then ultimately what we're going to be looking at here is this conductivity changing along the surface, and we can see the potentials changing based on the actual conductivity that we set. So the higher the conductivity, the more the discharge can actually stay at the potential of the electrode that we use to charge up the system. So you can see here that the discharge is actually more red than the one on the left because of the conductivity. If you have it basically at the conductivity of a metal, it would just be at the same potential as the electrode that you have here on the system. And then we're looking at the fields, so you can see that there is current flowing. There is a pretty high fields between the top and through the dielectric. There's actually a conductive ground backing under the dielectric. And then you have the nodes that contributed to the discharge process. So it's called arc node, and you can see it over time just propagating as the discharge propagates. So we use the empirical model to create a conductive path between the two electrodes and understand what the breakdown voltage is for the system based on the inputs from data or from papers that we know about air breakdown and things like that, and how much surface roughness would or dust or things like that would increase the breakdown voltage along the surface. And then you can monitor the breakdown potential over time. Here you're seeing it at the nanosecond time scale, and you can extract the breakdown voltage in the system for each simulation. The continuing current will depend on what the post-breakdown conductivity is set for the system. So for a full flashover, more complex conductor, you can do this for a much higher high voltage system with the dielectric here. So you have two conductors with a white dielectric that separates them and keeps them isolated. And then you have a vacuum around it, and we're creating slices now pretty often in our systems to kind of speed up the simulation process. So this is a 3D model, but you can create a slice and still kind of get the same system. And it's really zooming in on the early stages of what you see in the image in the center here, where you have a full-on arc established. So just to understand how that gets generated and what the breakdown voltage is for this is the tool to do it. In this image, you also see some other effects like corona discharges and things like that. And we have tools to also assess that based on the geometry and the problem of interest. So you can see here we ramp up the potentials in the fields, and then the dielectric will actually change over time at much longer time scale. And then what we saw was some surface enhancement effects where we have the discharge and the creepage happening along the surface of the dielectric. And then slowly we are getting more and more arc or nodes that are arcing, and we're able to understand we're ultimately changing the whole field distribution and arcing the whole air around the system. And so this is why you're seeing it kind of blow up and getting the whole air arc, just like you see in the image on the left where the full arc is established. What we really care about is typically is trying to stay away from any of the first nodes that are contributing to the discharge process. One thing that you're also seeing is that you can see the discharge skip the surface and move on to some of the other nodes as well and skip some of the geometry here. This is part of this enhancement field factors that we have that can be set both for tangential and for surface enhancements. So this was the STM. I think it's a very useful tool to run creepage and clearance problems very efficiently in various media. But if you want a higher fidelity model that considers full plasma, ions, electron tracking, and collisions and reactions, this is where looking at the particle in cell, CFD, and the reaction solver becomes very important. This is also in the FEM. It actually leverages a lot of physics. This is where really the multiphysics comes in to get this this level of fidelity. So we have the electromagnetics, so we've already talked about the quasi-static and the full wave solutions. And then we have the electromagnetic contributions from the plasma itself. This is done through the space charge contribution, but it can also be done through a conductivity change of the media in which the gas is due to the mobility of the electrons and ions in the system. So here you're seeing some of the charge screening methods that we have implemented in the tool and some of the implicitization schemes that we have as well. And then the other physics is how do we track these particles that are moving around in the system? And we're using a technique called particle in cell. And then we also have a fluid solver, so an actual solution to Navier-Stokes equation. And then we have a gas reaction solver, which is a Monte Carlo collision solver to be able to extract the energy of the particles that are colliding from the set of particles that we're tracking in the system and update properly the density, energy, and momentum of these particles after a collision occurs and the charge conservation, all that is present in the system. The PIC solver is a tool that allows us to track a statistically significant number of particles in the mesh. You can imagine that there's no way we can track 1e to the 20 electrons per meter cube in some of those models. Computationally, typically it's done by making sure that you have enough particles at each mesh element to properly sample the energy of the plasma in that mesh element. So typically 10 is at least the number that we go for per mesh element per species, so that we have a proper distribution of the particles in that system. And then at each time step, we can properly understand what the energy needs to be and sample the energy wave spectrum of these particles. So we can do that with the PIC and the fluid solver. The fluid solver is a continuum, so we don't have to worry about that. But having the ability to do a hybrid method like we do here by having both PIC and fluid allows us to deal with these transition problems in terms of pressures, where if you want to deal with rarefied gases where CFD is no longer valid, you can use the PIC. If you want to model very highly dynamic electron, even in a higher density plasma, you can use the PIC and then model everything else like the ions and the background species and the fluid solver, and really focus on getting the proper energy distribution for the electrons in the system using the pick. The pick is really the best way to get the accurate solution for the energy distribution of the electrons, even when you're dealing with higher densities in the system. And so that's why the pick is very critical, because it really helps us solve that problem and get the proper sheaths and the bi lengths in the system due to the electrons moving around very quickly at each time step. So what does it look like for a discharge problem? So this is very similar to what you just saw. Two electrodes, one red, one blue. And then in this case, the gap size is 1 millimeter, and we're looking at nitrogen. So we are tracking here the nitrogen gas, so the nitrogen molecules. We're tracking ionized nitrogen, nitrogen excited nitrogen, single nitrogen atoms, electrons, and the collision between all of these species. And then we're, in this case, modeling the changes in conductivity due to the plasma. We don't really care about the space charge effect of the discharge, but more about the conductivity changes. And so this is what we would call air conductivity and how that changes over time. And then we're able to model that based on the electron mobility and ion mobility that we have in the system. So we have a 2D method on the top where we create a slice of the 3D method in our mesh. And then we have a 3D mesh on the bottom here, which is the 3D model. They both run and give us the same solution, but one is 7 times quicker than the other. So if you don't care to go 3D because you want to simplify the problem, you can do that. This is going to work for any gas pressure, so you can change the pressure very low because we can change things to the particle and cell solver. In this case, we're dealing with about 1 atmosphere, and we're able to see what the breakdown voltage is in the system over time. And we're tracking the electrons, all the charged species, and the neutrals as well. And so we're able to give you a plot of what the electron density looks like, what the conductivity looks like, what the nitrogen density looks like, and the temperatures for each of these species over time. So this is giving us the highest kind of flexibility in terms of having first a conformal mesh on the electrodes, but also being able to change it to apply it to any gases that you can have the reactions for. And then it is, at the end of the day, an electromagnetic solver. So we do capture the currents flowing through the electrodes and the fields as well inside the gap. So here we're seeing the ramp in the fields and then the fields associated to the discharge itself. So you can see the field enhancement next to the spark and then a much lower field value inside the arc itself, which we would expect as we now have a conductive region within the arc. So this is accessible in our library. We have added the 2 gases that we validated for this solution. So the hydrogen and the nitrogen that we validated for those small gaps. Those were very small time scales. We're talking about nanosecond pulses, so in small gaps. This can be run in vacuum as well. So if you have E-field emission or thermionic emission, we can also solve for this in the particle and cell solver. So let's talk about RF discharges, not just electrostatic discharges, but RF discharges. In this case, in an RF discharge, we're basically driving electrons back and forth between 2 electrons enough to create more and more ionization with the ions that are in the system. And then the ions that are present and the electrons are going to create a space charge distribution that will move around and accumulate charge near the electrodes. That's called a sheath, and that sheath will screen the fields that are actually seen by the plasma inside the chamber. Even though we're applying an RF field, the potentials inside the plasma are going to start reaching a steady state solution due to the fact that there is a sheath being formed. And the other thing is there's going to be a bias that is applied to the electrodes in terms of voltage and current due to the fact that there is a current that is induced by the plasma onto the system. And so this is what we call a DC bias due to the plasma. And we can use our new circuit solver and charge that is released this summer to be able to solve for this bias offset that is present. So you actually couple a circuit solver directly to the full wave solver. It is slightly different than what we'll see in a little bit, where we couple a circuit solver to the M harness solution in the FDTD. In this case, it's directly coupled to the full wave solver And so we have this interface to exchange current or potentials with the circuit solver, and then we can use it to drive the voltage or the current on a given surface for a given electrode in the system. And so on the bottom right here, you're actually seeing the plasma potential on the inside, the potential that is kind of reaching a steady state over time, and then the electron and ion densities that are moving around, as well as the electron temperature near the electrode that is happening due to the sheath being present. And so over time, we're reaching a distribution of the plasma that is in this case expected and validated, and then you can see here the potential reaching kind of this stable 20-30 volts that is expected over time once we reach the steady state of the solution. And so we're able to get the proper bias due to the and ion densities and electron densities in the system. The other type of discharges are just electrons emitted from electrodes, right? So when you have enough fields or an electrode gets hot, you can actually strip out electrons out of an electrode. In the PIC solver, we have the ability to get to mimic this effect using some surface emission models. We have a thermionic emission model. We have now a brand new space charge limited emission model as well, so that we can account for space charge within the emission model without having to resolve the space charge near the electrode. And then we have also just simple inlets and outlets for electron and ion densities. And so these models are very key to be able to inject electron in the system due to very high fields. Electrons effectively will tunnel out of the metal and come into the cavity or into the vacuum. And we need to be able to solve that efficiently. And so this is what those inlets are for. And so you can run the PIC without electrons or without ions or without neutral gases, just with electrons, even just with ions if you wanted. You also can run it just with neutrals. And if you want to model a rarefied neutral gas moving around into a chamber, you can do that as well, right? That's what the PIC solver is for. In our case here, it is coupled to the electromagnetic solver, and you effectively want to model the proper space charge contribution for each of the charge species. And so this is what we can do here with the tool. So let's go back to this model here. We looked at a flashover simulation. We can actually run a flashover simulation using the PIC solver and the fluid solver. So you take what I did here is I effectively took the nanosecond pulse tutorial that I just presented earlier for air. You can see the environments that are generated here. Each of these species, you have to specify what kinematic model you want to use to track them, either the PIC or the fluid, and it's selected within the system. And you can also select if you want which type of electromagnetic plasma model you want to use, if you want to use the conductivity of the space charge problem. So for discharge problems, we care and use the conductivity model for the plasma so that we update the conductivity in a given location. The space charge contribution isn't as important as the amount of current flowing through the discharge itself. So we really care about that conductivity change. And what is going to happen as we ramp up the potential on this red electrode, we're going to get a discharge flowing along the surface. So there is a field enhancement due to the ground backing under the electrode, but there's also a triple point junction here that will have field enhancement and a higher chance of discharging. So we expect the discharge to really happen from the electrode and the geometry of the electrode and the field enhancement in that location. I'm applying 10 amps onto this location, and this will just drive current flowing through the system over time. So this is what it looks like on the left. This is the electron density over time, and then we have the cathode potential here. So we are able to see the cathode potential being steady, and it's staying relatively flat and slightly increasing, but you don't really see it on that scale. And this is maybe by like 100 volts over time. This is due to the fact that you have to push current through the discharge as the discharge propagates through the electrode and through the gap and along the surface of the dielectric. And we're able to see the electron density change over time and staying present. And then as you actually reach the other side, you actually see the field between the tip of the discharge and the electrode get very, very high as the spark reaches closer and closer to the gap. So you're going to get an acceleration of the discharge once the field gets very high, even probably some electron emission from the electrode itself due to the fields being so high between the tip and the discharge. So it happens very quickly, and then boom, we form the conductive channel. And so now the conductive path is there, so the potential just drops between the two electrodes. So we're tracking a lot of things to do this, all the species that we talked about. So we have density 1, density 2. We have the temperature of the ions and electrons at the surface. You can see very high temperatures of the electrons just where the tip of the electric fields are very high. You can see ESV here. This is the field value that I'm talking about that increases over time as the gap effectively gets smaller and smaller as the discharge gets to the other side. And then sigma is the conductivity of the medium that we're tracking. So we're able to see the conductivity of that discharge changing through time. And the fields Z here are very high, effectively keeping also the track along the surface of the dielectric. What's very interesting is it is coupled to the fluid solver as well, right? Because some of those species, like the ambient nitrogen, the air, effectively the air is also there, and there is heat that is imparted onto the nitrogen molecules that are much denser than the actual amount of electrons and ions in the system. And so this heat we can track over time. We can calculate, depending on how long this flashover lasts, the heat imparted onto the discharge. And here we're seeing not much heat happening, so you could actually kind of not get burnt if you were to get zapped by this process, because the timescales are so small, there's not enough time to transfer enough energy to the nitrogen. If you were to sustain this over a long period of time, you would actually start heating up air, and you could see air rising in terms of flow. So in my opinion, this is really one of the most fundamental ways to solve discharges. I think it's state of the art in terms of the ability to model breakdown in any types of gases, any pressures. There's a lot there that you can consider and have to add in terms of the modeling of the gas and the reactions that are present to get the right solution. But there is a lot that EMA can always help with in terms of making sure that you have the right reactions present in the system. Again, we can work this in vacuum. If you're just wondering about much lower pressure environments, we can do it. And then with the circuit solver, we can also start generating much more effective waveforms than the ones that just a simple current or voltage boundary condition. We can drive this with a power supply and some other types of waveforms that are present. So it's a very polyvalent solution in terms of being able to model various types of discharges. So now I'm going to go and kind of focus for the rest of the session today on the discharge capabilities in the FDTD. So the FDTD is designed to model much more complex geometries than the FEM. The compute time for some of the simulations that you saw earlier are on the order of hours, or even maybe like overnight or a day, to be able to run such a high fidelity simulation of a discharge, which would be very tough if you're trying to model maybe a secondary arc on an airplane or even on a cell phone, and understand where a discharge can occur and kind of the consequences of that on a much longer platform. So we have a more optimized model in the FDTD, but it's very specific for modeling discharges in air. We do track the densities of the species in air, but all the ions are treated as one species and the electrons as another species. And then we can track also the negative ions if there are any in the system. And then we do have momentum conservation that accounts for the effects of the fields on these particles as well, which we need to properly model the Townsend avalanche process. And so all this is optimized to be running very quickly alongside our electromagnetic solver in the FDTD. You have the ability to change the humidity content and the pressure, but the variation allows you to go up to 100,000 feet altitude. So in the FDTD, things are pretty easy to set up. The error breakdown region is going to be just in terms of inputs, It's going to be just the air density and the humidity, and you can actually click a sub-region of the space that you want to model, which we call the air breakdown region, and you'll find it in the EMA 3D section near the domain. And then in our case, we are driving here also with just a current boundary condition into the system. We're injecting current onto these electrodes that are present. These are bus bars. There's actually 4 bus bars per set that you see in the system. And then we're expecting to monitor where the discharge happens between those 2 electrodes. So this is us just setting a pretty simple source onto this model that is made out of just pure PEC material. We have an animation probe. We have a voltage probe. You can see the plus and minus in the center here. And this simulation can be ran on GPU because we've accelerated the FDTD to GPU, so things are running very quickly. You can see here some of the results that are being generated by the animation probe. This is a plane that we place to be able to track the location of where the arc discharge happens. As I'll introduce in the next hour, we'll be able to see the breakdown due to, in a 3D probe that we actually have, which allows us to figure out where discharges occur, not just anticipate in the first place where they might occur, which is what we had to do in the past when we placed those animation probes. In this case, we were able to see the discharge happen, the current flowing through the discharge, and the plot of the voltage through the system. And so we have the breakdown voltage and the continuing voltage due to the arc resistance due to air being present in the system. So the workflow is very simple in the FDTD. In the FEM, you have to define each species of your gas and the reactions. Here, it's all defined and present and hard-coded inside the tool. So it really helps us quickly expose areas of vulnerability in the design, such as the location of secondary arcs, not just the first arc due to the non-contact ESD gun being applied to the system. We capture displacement currents due to geometry charging up and down, and also charging and discharging, and any coupling that happens of the fields through seams and apertures that could be present, for example, around a button on your cell phone. And then you can predict the coupling voltage and current waveforms that are happening from the discharge due to the fact that we properly reproduce the impedance of the target that we're actually zapping in the system. So instead of idealizing the waveform for an ESD that you typically may get from a standard, in this case, the ESD is really dependent on the gun and the device under test. And so we really have to consider these two to get the actual current waveform onto the system. So this can help us limit over designing diodes based on just an idealized waveform and making sure that we properly get the right current that is passing onto the system. It is a quicker simulation speed than the FEM, but it is, again, limited to air. So let me introduce you to what it looks like to reproduce a full test standard inside Charge Plus. So we have what we call our digitalized ESD generator, and it's based on years of work and refinement in terms of getting the ESD gun to reproduce standards and be easily applicable to industrially relevant problems. So we started, Jennifer actually started, I think 3 years back, rented an ESD gun and had a target, a 2 ohm target, and then scope in the system. And then we had various ESD gun tips that were present, the contact ESD gun tip and the non-contact ESD gun tip. Our first model is on the right here, and you can see that it was very large. We had a lot of geometry that was present that we need to properly capture the inductance of the ESD gun and the components inside the gun. We had the ground strap, which has its own inductance. And this is needed because in a full wave solver, when there is a spark or a flow of charge between the source and the ground, it's going to create fields that are going to couple to the strap. And these fields are going to be changing what the actual waveform looks like once you look at the current through the arc. And so by modeling this, we can actually solve for this as well. But this isn't very feasible in terms of using this model onto a very small device, because all the problem space is actually taken by the ground strap, which doesn't allow us to resolve efficiently a PCB, for example. So we created a much simpler model. We'll call it the simplified model, where we idealize the ground return strap with some circuit parameters, lump circuit parameters. The FDTD has thin wire models that allow us to set RLC terminations on them. And so that allows us to create relatively simple circuits. We also have switches for these that you can put in conjunction with thin wires. And that allows us to kind of, again, create simple circuits in the system. If we want to go beyond that, then we can use something like Nexxim or a SPICE circuit solver that's integrated to M-harness. But within the FDTD itself and Charge Plus, you have access to the thin wire tools to be able to set these components. And then you can see now that we just keep the ESD gun tip, and you can easily swap it with a different geometry if that's what your generator looks like. So you can recreate your generator, your ESD generator that you have in your lab very efficiently, the same way we have here. We can teach you how to do that and calibrate your ESD gun to the one that you have in your system. A lot of customers may have very standardized or proprietary ESD generators just to make sure that they have the control they want over the ESD waveform and the repeatability they need to be able to test a lot of devices. So in our case here, we just did as best as we could to model the one on the left. So what does the validation looks like? So in the colored waveforms, you see all the different tests that we took in the lab that you saw earlier. You can see a lot of variation in one test to the other. This is pretty well known due to changes in humidity and temperatures and designs and electric components in some way, charging up slightly differently maybe in the gun. But there's a lot of variation from one test to the other. And so that's a problem. And that's why creating your own generator in your lab might be something of interest. So you have a lot of control over the lab environment. Nonetheless, you can see that with the full model, we have a very good match between the first peak amplitude and the second peak amplitude. And we also get some of this oscillation in the second peak, which is this electromagnetic field coupling to the ground return strap. We can't keep that strap, so we have to idealize it with a lump circuit model, and you can see it being much smoother on the right here. So we just tweak the circuit parameters in our model to be able to match the shape of that waveform as best as possible. So now we can properly get the rise time of the first peak, the amplitude of the first peak, and the total energy under the waveform, which is key to be able to make sure that you don't get a discharge or a secondary arc down the line. And this is all done on a 2 ohm target for a 15 kV discharge with a fixed gap size. Ideally here, we don't have any motion of the gun. It's just, you can imagine that you already approach the gun at a fixed distance, and then you discharge it by flipping a switch. And so it will be very consistent in the simulation, which might not be as consistent in your testing environment. So one of the key here is that we can reproduce the standard waveform, but ideally that's not really what we want, because what we really care about is what the waveform looks like when you consider all the capacitances, parasitic capacitances that are in the system, the impedance of the device under test, the charging elements of the ESD gun, the inductance of the wires. All these need to be considered properly to get the actual waveform. And obviously the arc resistance and the modeling of the non-contact ESD itself. The tip of the ESD gun also plays a role, this geometry, and the parameters that we have inside our code to model the air is very critical to get the proper waveform. So this is why this is a very complete solution, and it's well vetted to reproduce the standards, but it will give you more once you apply it to an actual device under test, because the impedance of the PCB or the cell phone is not 2 ohms, it's going to be something different, and that will change the waveform. So we inspired the circuitry inside the ESD gun based on what you see here. A couple of things to note is here the target is represented as a 2 ohm target. So this is what you would change when you do a full wave solution and capture the material properties and the geometry associated with your device. We have the typical resistance of 330 ohms that we see in parallel with some of the capacitor and that is present for the ESD gun. This will actually shape your first waveform in your peak. And then you have the ground return strap that is approximated with an inductor. I think we said about 20, I don't know, it's somewhere here, 2 microhenries. And then this will help us shape the second peak in the waveform. And so by tweaking these parameters, and we're able to reproduce the idealized waveform from the IEC standard, and we can change it based on the voltage. Very easy, you can change the voltage peak in the system and then change what the waveform will actually look like for each of these tests that are defined in your standard. So the rise time matches very well, and then the energy under the curve as well. And you can see here a comparison between the charge simulation versus the standard for this very simple, simplified ESD gun in the system. Talking about rise time, we've done a lot of validation against the Rompe and Weisel model for the rise time. This shows us that the air chemistry parameters that we have in our system work very well for modeling the initial parts of the discharge and the breakdown voltage and the currents flowing through that first peak. So we can do that for various arc lengths. Here we can see a validation from 0.8 to about 3 millimeters, depending on the type of discharges and compared to the Rompe and Weisel model. So 0.2 millimeters is a very small mesh. So how do we solve this problem? Well, we have variable grid, which allows us to create a smaller mesh around the PCB. We also have GPU acceleration. The ESD gun, you can't get away from it if you want to get the proper waveform. So we have to be able to mesh the components on the PCB, the layers, the separation between the traces, as well as the gun itself. And you can see here some of the compute time. On the bottom of this table, on the top of this table, you are seeing that it takes about 15 hours to simulate these simulations on CPU, and it's about 5 times faster on one GPU. But this simulation can be easily parallelizable on multiple GPUs as well to speed that up even further. So there's a lot of different tools here that we can use. And so with the GPU, we can actually do a variable mesh, use a 2 millimeter mesh for the ESD gun, and then a 0.2 mesh for the PCB itself, and solve this in 4 hours on a GPU. A quick look at what the results look like before we go into the details of setting up these types of simulations. Here you are seeing the air conductivity. So this is due to the electron and ion mobility in the system. And obviously there is current flowing through the conductive path that is formed here. There is a discharge that is happening from the gun to a PCB enclosure, and then from the enclosure down to the chip and the board underneath. And there's a secondary arcing happening from the board down to the bottom of the enclosure because this was charging up and floating in the system in some way. And then we have a path for air to just keep ionizing in various places. And we're using these cut planes to kind of probe the discharge and the air conductivity in various locations. We do save the data in 3D now. As of 25R1, we have HDF5 file format to save very efficiently the data. And we can pass on that information to NVIDIA Omniverse, and we can create very amazing animations to visualize what the where the arcs are happening, how much current is flowing or fields are propagating through the system. So you're seeing conductive displacement currents along the chip, as long as actual current from the conductive path that was generated from the discharge of the gun to the chip in the system. So we can give you a lot of details on where all the problems could occur. Ultimately, you want to understand how each of the components on the board are responding to this discharge that is happening at the chip level. And if you can change the properties of one of those components to be able to understand if the current of the ESD changes, or if you're able to limit current flow down the line due to a diode that you placed in the system, like a TVS, for example. Let's keep going. So We're going to walk through 3 examples. Each examples are building upon each other. We are showing you how to assign materials, sources, meshing, and how to kind of tweak some of the tutorials that we already have in the tool to get to those higher levels of complexity in your ESD analysis. And again, the key here is to no longer really approximate the waveform. It's to get the exact waveform that will be applied to your device based on the discharge, get the location of where the arcs are happening and at what voltage the arcs are happening. If you're doing a 15 kV or 8 kV discharge, if you're doing a contact or non-contact, all the geometry needs to be considered, and the FDTD is meant to help you do that. So we're going to run an air ESD simulation on this PCB that we just saw. It's enclosed inside an enclosure that is metal, and it is set up in a location that is just under the ESD gun, and that enclosure is actually on a test bench that is grounded. And we'll be able to see where the ESD happens, and this is one of our tutorials. So part 1 of the ESD tutorial is available from the user manual, as I described earlier. This is something that we call part 2, and then we have part 3 and part 4 that we'll talk about today as well. I'm not going to go in too many details on this one because we have this step-by-step already available. So in this case, you can actually see we have our ESD gun. You can take the ESD gun from the tutorial, the one that is already calibrated to a 2 ohm target, and then you can either recalibrate it to match your test setup, or you can just put in your device under test and replace the target with your device under test, which is literally what we did here. We imported the PCB, and then we have the enclosure that is present, and then we place the a specific distance out, and then we set the source to match the amplitude that we want for the ESD gun. So if we zoom in on our PCB, we have our IC, we have various traces, we have the materials already assigned. This was all done using the EDB import tool, which we have optimized over the last couple cycles. One thing that we really recommend is to position the PCB first using the move handles of the EDB tool before it's much easier to move around than having to move the PCB after the board was imported. It's a little tough to do that when you have all these lines and the components to move around in the material assignments. So just position it in the right place first and then import it. All the vias, layers, and traces are going to be present. And then you will have the ability to, the materials will also be assigned automatically during the import process. And then all the RLC components will be assigned a thin wire as well. Sometimes the import might have a little issue. We really recommend using the SI Wave export tool, and then for generating the EDB file, and then using that EDB as an import. So now the next step is going to be to set up the breakdown region on where we expect the discharges to happen. So we are going to move around the breakdown region, and it can be a subdomain of the actual full electromagnetic domain. It is slightly computationally more efficient to do it that way. And it also helps us not ionize places that are not ionized in real life. For example, where we drive the source of the ESD gun, there's going to be some very high fields around the source that we don't really care to model numerically and understand the consequences of it. So being able to define a location where the background is air versus linear is very powerful. This will be kind of the place where we track air conductivity, ions, electrons inside the system. So this is going to be around our enclosure all the way up to the PCB, to the ESD gun tip as well. So once you've done this, we have the ability to look at all the components of the ESD gun, and we can start tweaking the ESD gun itself. Obviously, we want to assign materials first. The materials is what will really help us understand how charge can flow around the system, around the target. This will help us also make sure we track the currents flowing through the traces that are defined as metal. And if you have some plastic, like in a plastic enclosure, it will definitely change the behavior of the discharge compared to a metallic enclosure. So the electric conductivity of that enclosure is key. So this is very applicable for any devices like earbuds, mouse, keyboards, cell phone with cases. You could think of cameras. I'm looking at everything on my desk right now that has a PCB inside a plastic enclosure. There's going to be a lot of risk of ESD and discharging to that device. So as you rub your feet on your carpet and move around, you have to really be able to understand how to mitigate this charge that could discharge to these components. And so the properties of the material that you choose will change what the actual waveform looks like. And so we need to make sure that we have the proper materials. We do integrate with the Discovery Materials database, as well as the HFSS Materials database and the Granta Materials database to be able to use all the parameters that you may have in these tools. And then the variable grid, this is where we define the mesh to be smaller in a given location than in another location. So here we're defining our domain. So we have our whole full wave electromagnetic model that encompasses the ESD gun and the test bench and the PCB. But then ultimately, we want to define a smaller mesh so that we don't short traces together at the level of the PCB. So that's where the variable mesh comes in. So here in this case, we can place the variable mesh grid region to be where the PCB is present. And this will allow us to refine the mesh in that location. One thing to note is that the FDTD needs to have a conformal mesh, and by that I mean that you can't have staggered cells. Like each of the mesh element needs to be connected at their corners or vertices. So this makes it so that the grid has to be very fine all the way through the whole domain, not like you'll see in a second when we visualize what the mesh looks like, but the refinement in one of the dimension has to extend all the way along the axis. And so it does help us refine the mesh size significantly across the whole domain, but it does, it's not something that you can have a growth that that is typical to FEM meshes. You have to deal with the way the grid grows in FDTD. So the next step in our process is to make sure that we set up proper probes. So we have a voltage probe that is present. We also need to make sure that we capture the current through the system. So the breakdown voltage of the arc and the arc resistance and the arc current can be done by setting up various probes. So here we have a voltage probe from the gun to the PCB. And then we can actually look at some of the various tools that we can use. So we also have the animation probe, and we can show you how to set that up in the next slide here. So the animation probes, you can use a cut plane, but you can also just apply it to the PCB traces itself. You could apply it to the ESD gun tip if you wanted to see current flowing on it, but it's not as interesting. What you could do is look at the ionization generated from the ESD gun tip using one of the animation probe and see if you're getting any arcs or streamers that are generated to the side and not just towards the target. Here we're looking at the current flowing onto the traces due to the ESD itself. So we can look at the PCB surface, and it will be looking at the current flowing due to the material properties that are set up on the PCB board and to the components as well on the boards. We have, in this case, I think a resistor on the board as well here between two traces. We're creating another probe for the air conductivity. And then that allows us to probe the 3D region for the air conductivity, so that if we don't know where the discharge is going to be, we can actually visualize at each of these locations where the discharge will be in the system. So this is our newest 3D visualization probe, and now we will show you in a second how to kind of visualize what that looks like as well. It is a lot more data. So when you set up the probe, I think you want to make sure that you look at the time step that you're using and the range of the data that you're saving in terms of computational time domain. So instead of saving, for example, the full microsecond of simulation, you may save maybe 10 nanosecond in the time where you expect the discharge to occur, or maybe based on the breakdown voltage that you got from the previous simulation, to be able to look at where the ionizations occur. Because it is a lot of data to save the fields in 3D, even though we're using a binary file format, which is about 10 times more efficient than the ASCII file that we had before. It is still a lot of data to save. So just be cautious when you use that 3D probe type. You can also sample the spatial grid every cell, every 10 cell or every 100 cells in case you have a very high resolution. That helps you downsize the size of the file significantly. And for the post-processing tools, it might be very important because some of the post-processing techniques and tools out there might not be able to handle terabytes of data to do the post-processing. So just being able to downsample not just in time, but also in space is pretty important. So now we're looking at the mesh. You can see this extension of the variable mesh that I was talking about all the way to the edge of the grid. So you can see that the z-axis and x-axis here, we have the 0.2 millimeter mesh that is extended to the domain boundary. But you can still see that a lot of the problem space is meshed at 2 millimeters, which is key because it would be very time consuming to run all this at 0.2. And then you can press start. Based on your settings, it will run either on GPU or on CPU. You can change that in the settings. And then here you can see the source voltage that we're applying to the system and the actual voltage of the discharge that we're getting from the ESD gun to the PCB, as well as the current waveform that depends on the dielectric enclosure that we have in the system, and also on the location of the PCB and the impedance associated to the PCB itself. And then you are monitoring the voltage across some of the components on the board. So here we're looking at the resistor R1 that is on the board that we set up as a seam. In this case, it's a barrier article, so we don't actually have to resolve that resistor in any way. It's meshed. It's using a subcell algorithm to solve for this problem, and then we can monitor the voltage through that resistor using the typical voltage probes. And so we created these animation probes. If you remember, on the surface, we have the electric current, and then this allows us to look at the current flowing through the traces based on the grounding schemes of the board. This was very seamless to import and to generate and look at. In terms of running the simulation, it took a couple hours, and the placement of the board was very easy as well. So to be able to run an ESD simulation with an enclosure so quickly is very powerful, including the whole ESD gun model. And then now we're looking at the 3D results of the probe. This is using the visualization tools within Discovery called Graphite. So the visualization arc on the bottom right of your screen. And then you can see the air conductivity being present. The air conductivity can go up to maybe 20 or 100 Siemens per meter, but you can see that if you lower the scale to about 2 Siemens per meter, you'll be able to enhance the visualization of the arc and where it's actually happening. And so we have a discharge here that went to the enclosure and then all the way through the enclosure down to the PCB itself. So this is what we would call the secondary arc from the enclosure to the PCB. And you can have tertiary arcs as well from the corners of the PCB down to the enclosure, as we saw maybe a couple slides back when we looked at the full animation of the system earlier on. So let's apply this concept to a much more complex geometry. So this is what you would do if you had your device under test that you would want to look at very quickly. You would, in this case, we're using a simple cell phone model with various PCBs and components inside the cell phone. The screen is a touch screen, so there is a conductive backing behind the glass. There is the board for running the PCB and also the board for running the phone. There are antennas in the system as well that play a role in what and how things propagate. So here we really want to look at that 3D probe in a lot of detail. We want to be able to manipulate where the ESD happens very easily and be able to remesh the simulation quickly and change the settings of basically the gap size that we're applying into our system. So we're looking here at the kind of taking the approach where we took the ESD gun, we brought in the geometry. So you would actually use the the import geometry function within the tool that would bring in the cell phone. And then you have the boards that you have to assign materials to. So you use our material assignments tool. So we have an enclosure here. We have the ports on the bottom, some of the microphones, the antennas. We have the PCB on the inside. In this case, we use the same PCB just so that it's non-proprietary and that we can see some kind of interesting features on the PCB. And then we have various components as well. And there is a pretty small gap between the button and the PCB, the button and the enclosure. So there is some air that can actually get ionized through that gap. And you can have ionization between the PCB and the other components inside the system as well. So it's important to be able to visualize that and understand where that is happening within the system. It's not because you're not arcing to the PCB that you can't get ionization due to various displacement currents and things like that that are happening inside the system. And then you can change the ESD gun tip very easily. So move it around. This will help you kind of reproduce your test setup environment. So if you move around here, we can kind of look at the angle that we set up. We have all the components, the voltage source at the top. We have the switches, the 330 ohms present as well. And then we have our ground return strap that is also modeled and connected here to our ground plane. And here, this cell phone is in this case, it looks like it's floating on top of the board. So there could be another discharge that could happen down to the ground plane as well, if needed. If it occurs based on the setup problem that you have in the system. So in terms of understanding the consequences of the problem, we want to make sure that we probe the proper simulation time and simulation range. So in our case here, we are running a waveform that will last maybe 50 nanoseconds total, because the key is the rise part and the pulse happening around 20 nanoseconds. And so we want to make sure that we can actually get the proper ionization happening inside the system. So make sure that in our simulation, we actually change the start time to capture all the ionization that will happen in the system and the secondary arcs that will happen in the system. So running the simulation long enough is key. So this is why we have a little note here on the charge time. Then just like we did before, we're going to set up the arcing region. In this case, we want to focus on any breakdown happening within the cell phone and between the ESD gun and the cell phone as well, to see if we're getting a spark happening through the gap for the discharge that we're choosing to model. We want to do the variable grid again. The variable grid helps us make sure that we have enough mesh elements along the PCB, but also enough mesh elements between the ESD gun and the target. To be able to get the proper breakdown voltage and proper current flow, we always recommend having about 4 mesh elements between your conductor and your target. This helps us solve for the fields accurately and also for the air chemistry accurately in the system. So that's where using the variable grid and extending it all the way to the ESD gun is important. You can actually select geometry and it will make the grid line up directly with the system. And you can see here that we've extended it all the way to the ESD gun tip to make sure that we get the proper mesh element count in the gap. You can also see that we have there's a small hole happening here between the enclosure and the button. And this is where we may have a discharge happening either above or below or even creep on the button before it actually gets into the cell phone to the PCB. Just like we did earlier, we want to be able to visualize what the currents are on the PCB. So we are going to look at the animation probe in a second, but here we're looking at the amplitude of the waveform. So if you want to change and run a 25 kV pulse, you can do that. I think 15 kV in this case didn't actually create a discharge. So if we wanted to understand and what voltage this would happen, you can actually either just do a constant ramp, or you can do and set incrementally the potential to increase until you actually get a spark in the system. So we've assigned all the materials to the components. This is the same EDB import that we did earlier that we placed within the PCB. And we're applying a probe here again at the surface for the current to understand, based on this discharge, which is not the same setup that we had before. In this case, we're going to get a spark to the PCB through the button, not just onto the enclosure down to the center, because the phone case has a different material than we did in the previous simulation. We'll be able to see what the current looks like based on the grounding schemes of the PCB and how it's connected to the phone inside the system. And then we'll still do a 3D probe because, again, our goal is to track down the location of secondary ionization in the system, because then you may have some, if you were to open the device up after you do this test, you could get some damage inside the system. That's how you would understand that there is secondary arcing happening. Or you could get a short or a spark that will trigger one of your components, sensitive components, and maybe kill signal in some way down the line. So to be able to understand any interference from a spark, you need to know where they occur, and so that you can mitigate them by either changing the placement of the PCB or adding some diodes in the system, for example, or change some of the component parameters. So the way we visualize the 3D probe can either be done through the previous discovery interface, but we also have a third way to look at the visualization of the results, which is called pair view. So this is one of the methods that we use to really look at the binary file that we generate. We have a plugin that is installed directly with our tool to interface with pair view. It will allow you to read in this HDF5 file format that you see here that is present in your simulation directory. This is how we save the data much more efficiently. And then when you load that data, you're going to have access to all the variables that are present and dumped by the solver. In this case, it's going to be the air conductivity, because that's the variable we chose to save. It's going to be downsampled spatially based on what you put in your input setup for the probe. And then you can also import here in pair view the geometry if you want to import the cell phone and the ESD gun, as well as all the stuff that you saved in the STL region. So you can see here we have the geometry plus our results data that is saved on this 3D volume. This allows us to kind of see exactly where in the geometry the discharge occurs. In pair view, we have a lot of things that we can do. They're called filters. You can actually right click on any of these data sets and do various processes with them. You can integrate the variables. You can create time annotations. You can also extract data in various places. In our case, we're actually going to change here the opacity of the geometry so that we can kind of keep the geometry in the background and highlight the location of where the air became conductive and where the discharge occurred. So here we're changing some of the settings of the actual results file. We're selecting the air conductivity in the coloring data set, and we can change the range. It will automatically scale the range to the whole data. As you saw, if you want to highlight, we want to make the upper range something like 2 Siemens per meter. That was something that helped us highlight the air conductivity in the previous system. Here we'll do 1. It will allow us to really enhance the location of where the air is being ionized in the system. So this is our first look at where the discharges are occurring, and we can see the discharge between the ESD gun and the button, as well as between the PCBs inside the system and all the way down to the PCB. Our time settings are at the top here. We're looking at 50 nanoseconds. This is kind of the sampling region that we saved. So pair view is very useful. It's a third party. It's free. It helps us kind of look at these HDF5 files very efficiently. but it takes a little time to learn. It's a new interface. You can change the color scale very easily. There is about 10 different color scales that you can choose from. And then this is where we have this thing called filters, where you can do a lot of things with the data, like clip planes, integrate, things like that. A lot of different tools that are available within ParaView. Here we're putting the annotation filter, and you can change the time that is being displayed using the format. So we're looking at 50 nanoseconds, so we just have to reformat the scaling so that we have the actual nanoseconds displayed here. So now we actually have the time visualized and we can see the first 50 nanoseconds of the discharge as we iterate through the file. Using the HDF5 file, we're really able to process and parse that data very easily. There's also some NVIDIA plugins to ParaView that will help you deal with even larger data sets and do all this rendering onto GPU even more robustly. And then you can save this as an animation. Typically MP4 is the way to go. It's much lighter in terms of visualization and space that it's used to save the animation on disk. So here is the results of our animation. We have, looking at the air conductivity from the 3D field probe, you can save fields, you can save space charge, you can save electron and ion densities. We are added a lot to the probe, and you can see here over time what things look like. So we have the initial ESD through the gaps. We have a secondary ESD to one of the boards that is next to the PCB. And then we even have an arc that is happening between the two PCBs as well. And so all of this is probably a lot more than we expected at first, which would be maybe just an arc to the enclosure. One thing to note is we did ramp up the potential of the gun to be able to get this much arcing. At 15 kV, we wouldn't have the same behavior as we did here at 24 or 25 kV. So depending on the standard, depending on your analysis, you're going to have different behaviors, and all of these can be accounted for in the tool and tell you where the consequences are. So how do you mitigate the ESD? And this is where coupling with a tool like Nexxim becomes handy because you can add nonlinear components to the system. And so this is where we can show you how to take this even to the next level, right? And size the response of the waveform or the test due to having a diode present or a different grounding scheme in your system. So we'll be able to compare the results with and without the diode that we're setting up onto the secondary PCB that we have in the system here. We'll also show you the new post-processing tool that we have within Charge Plus, which is called EMA 3D Connect. And so Connect is a tool that we have developed in-house to do some quick post-processing of a lot of analyses that you may have in parametric studies, for example, that you can set up in the tool. So this builds up on what we just did. We're going to open the tool, and then we're going to move the ESD gun. We're going to change and create a cable with a 50 ohm termination. And then we're going to be able to place a diode on that cable. This actually requires EMC Plus because the integration of the FDTD with a circuit solver is done through mHarness. And mHarness is only available for EMC Plus and not for Charge Plus. So here in our case, we're kind of using the same thing, but we're moving the ESD gun on a different location on the board. And then we're also kind of setting up this connection of this board. It's basically your connector through the charging port of the PCB of the cell phone. So it may be one of the controllers for the battery system, for example, and you're connecting this to make sure that you can resist a surge from a discharge of some sort and understand what the current flow will be through that grounding scheme that we've set up. Same thing as before, we have to set up the breakdown region to make sure that we properly monitor all the ESDs in the system. We want to make sure that we have the animation probe and the 3D probes. And we're going to be looking at air conductivity and the 3D probe, just like we did earlier. It's just placed in the location where we know that we're going to have the discharge here around the ESD gun tip. So in this case, we're using mHarness to be able to set up the conductor. So this will be happening in the harness tab at the top. In the harness tab, you can set up a pretty simple conductor. It is basically a beefed up thin wire, a solution that we have, just like we did earlier. The thin wires are not connected to the circuit solver, only the mHarness solution. And we can exchange the current and voltages at the end of the conductor with the circuit solver to be able to place a component of much more complex than the linear components that we typically do for thin wires at the end of the wire. So here we're actually looking at how to set up the conductor. You can go to some of our definitions that we have. In this case, we're doing a 26 gauge wire. You can create your own. It's going to have a jacket if you want, various resistances, and then you can model skin depth effect. There's a lot of different capabilities that we have inside the mHarness tool. And then you can set the terminations. In this case, we're going to set up that 50 ohm termination at the end of the tool here, and you can see that we have a lot of various configurations for the terminations as well in the tool. So it's going to be called segment, and then we have the junctions and the termination. This is how we keep track of the various conductors within the harness. You can add much more to this. If you wanted to add a signal like a coax, if you wanted to add an additional wire to the harness that could be present like you would have in a USB-C or so on, all this can be added to the tool as well. You could actually, as one of our demos, we've seen how to set up a USB port and a USB cable. This is something that you can see for EMC Plus and understand how an injection of current on such a connector can actually get and propagate through the PCB. While this is slightly different, we're looking at what the response is of a diode to the ESD and the non-contact ESD onto the system. There is some synergy there where you can learn on how to use mHarness in some of our other tutorials for EMC Plus. So for understanding the currents and voltages flowing through the cable, we have specific probes. You can use our full wave probes and put a current probe around the cable. We will be able to use Ampere's law to be able to assess what the current will be there due to the fields in the full wave solver. But we also have probes that are present and that we can set up onto the harnesses themselves. So here in our case, we are going to be selecting and creating a voltage probe on at a given location along the distance of the segment, and then you can select the termination that you want to probe from. So in this case, we're looking at the end that is connected to this piece of geometry under the ESD gun. And then we're setting another probe on the other side as well. So this will help us understand the voltage difference before and after the diode is present and placed inside the system. When we mesh this just like we did thin wires. We have to mesh the harness, and it's a linear element mesh. As you can see here, we have a line that is meshed explicitly, which is going to be the path of where our segment is present. We have some rules on how this segment and cable can interact with the rest of the geometry. So there are some deconfliction algorithms inside our mesh engine to be able to handle the path of the cables through the mesh geometry. These are part of some of the typical tutorials for EMC Plus, and we can definitely explain how these methods work and depending on some of the routing that you may have in your system. So now we can look at the results. So we have our probes that are set up. The probes for the mHarness solver will be also saved in the same location where our results are saved for the animation probes. We have simulation, and we have the results for both having a diode and no diode in the system. In this case, we're looking at the results without the diode. We can import the results from the EMA file. And then we can select the time steps that we want to look at if we're interested in looking at the results from the 3D probe within Discovery. In our case here, we can go either to Discovery or Peer Review with the 3D probe. but we're really mostly interested in the cable voltage from the results without the diode present. So this actually doesn't use a circuit solver yet, but we're able to see the voltage in that cable. You can actually add a shield if you wanted to the cable to make sure there's no coupling through some sort. It could be a twisted pair, it could be various things, and the results will depend on what the harness composition looks like. So it's very important to get the proper harness composition as well. So this is our voltage without, and we want to see what happens when we put a diode onto the system to make sure that we can suppress the current flowing. So how do we add a diode? We have to couple to the circuit solver. The circuit solver that we have under the hood is Nexxim. This is the Nexxim circuit solver. While in charge, I talked about a circuit solver for 25R2. It's going to be NG Spice, so slightly different solvers, but at the end of the day, the principles are kind of the same in terms of what our goal is and our capabilities in terms of being able to set up sources and various components inside the system. So you need to go ahead and select the Nexxim termination and the Nexxim tool, and then we can actually add that to our harness and to our conductor. So here you go to M harness and you can select the circuit termination. You will apply it to the end. Instead of applying like the way we did for the 50 ohm, you would actually apply this circuit termination, and we have a circuit termination editor that comes up, and we can see the end pin of the conductor, number 2, which is the only one that we have here set up. You can select lumped elements. You can also just import. You can use some of the specs that we already have in the tool. In this case, we're going to import the file for a specific diode that we have in our tool that maybe we got from Little Fuse, for example. So we have a diode file that is present, and it will be represented here with the proper schematics. We can place it in line or in parallel with one of the resistors to our ground, and this is how our termination is set up in our tool. You can click and drag, and the circuit is now set up with the schematics of the diode of interest that is now placed right here in our cell phone. Okay, so the next part is to look at the results of the simulation. So we remeshed, and then we pressed start, and then we have now 2 sets of results, the diode and the non-diode results, and we want to understand what the effect on the current of the arc is, but also if it was able to suppress any flow of current through the system due to the diode being present. So how do you launch Connect? It's next to the import section, import tool. Here we have the Connect button. The Connect tool will allow you to launch our new user interface for post-processing. So here you can see EMA 3D Connect and the results for the no diode tool. We can actually import many different result types, and then all the different types of results that we have for a given simulation will be also available here as well. So if you want to download EMC Plus results, select the parent directory of the results, and then all the results inside it will be loaded as well. The way the Connect works is we have this flow of information that we deal with, and it's dealt with the use of pipelines. So we can do a lot of things like with the results, similar to what you would do in pair view. So you can take and drag the arc currents into the geometry, into the window, and it will automatically plot the results for you. So it's a very quick workflow, but this is associated with a pipeline where we created a source node for the data and an effective XY plot chart that is connecting the two. So you could actually create many different charts and 3D visualization tools, and you can pipe the data into those charts and each of the nodes that you see there. You can also have multiple results piped into the same chart so that you can overlay them. So it really helps you deal with a lot of data at once efficiently. So in our case now, we want to look at how things look like when you have the diode and not the diode. So you can click the arc current from the other directory, and then you can drag it into the same chart. And now you have the ability to overlay the two results. And so we can see here the current changing in amplitude due to the diode being present in the cable in the system as well. You can change the labels very easily. You can change the line style, put some markers as well. You can highlight which plot you want to look at. If you have a lot of data sets to overlay on top of one another, this really makes it easy, and it's tailored to a lot of our solutions, EMC Plus and Charge Plus, but it can be used to visualize other data as well. The other thing that we want to look at is the voltage through the cable. We go through the same process, and then here we can see that we've attenuated the voltage completely through the cable due to the diode being present. So we really suppressed that voltage through the system. I think this is current. Sorry. So yeah, this is just a quick introduction to Connect. You can also do 3D plots in Connect, not just XY charts. So you could do actually a lot of the things we did in pair view and visualize the 3D data as well with cut planes and clip planes. This is automatically installed as part of EMC Plus and Charge Plus and is really meant to handle the post-processing of some of our results when you have a lot of results at once. Okay, I think that's it for the session. I do know that I presented a lot of information, and I would be happy to answer some of the questions that may be present.
Yeah, absolutely. Thank you for that presentation, Kevin. And yeah, now we're going to move on to the questions that were posted in the Q&A. And if you have a question that you haven't posted, please feel free to do so now. So the first question is, you mentioned that you can do simulations in 2D and 3D, and that 2D is 7 times faster. What simulation or what situations are important to run the simulation in 3D, and what are the benefits of using a 3D simulation other than it being, or actually, what are the benefits of using a 2D simulation other than speed?
I think that's pretty much the only benefits. You remove a lot of fidelity that you may have in your 3D CAD model. There may be some features that will add some asymmetry in the discharge phenomena that you want to be able to capture. You may have some B fields that may be asymmetric, things like that. So I think going 3D is what the solver was designed for, and solving this solution efficiently in 3D is what it's ultimately the goal. But going 2D really is meant to kind of get those validation problems that a lot of other tools have gone through and done also in 2D as quickly as possible. So maybe the other way is to just be able to reproduce other methods that have been used in the past that weren't able to do it in 3D as well in 2D.
Perfect. Thank you. Could you explain the variable mesh a little bit more? Can you use several different variable meshes within the same model setup, or are there any situations that you can think of where it might be necessary to set up multiple variable meshes?
Yeah, that's a good question. I think at that point you would want to think about how to optimize your compute time. So you could just create one for everything, and then that would help you just run the problem with a variable mesh on the whole cell phone and not have to worry about creating one for various PCBs. But one place where you can actually create 2 variable meshes would be if you have 2 electric components separated by a long distance on 2 different tabletops, for example, or you have an antenna that you want to model with high fidelity that emits a lot of radiation, and you want to see the coupling to a PCB further away. You can use variable mesh grids two different ones in various locations to be able to help out with that. So that's very useful. The other thing is that that variable mesh tool can be used to fix the grid size and make sure that the grid doesn't change in size in a given location. So at today's today's capabilities in the tool, you cannot have the mesh change in size when you're using mHarness and the harness and the transmission line solver. So that means that every time you have a harness like we just did here in our simulation, we in our demo, we want to make sure that we fix the grid in that location to not change in size. And so you can actually create and use the variable mesh tool to encompass all the cables and make sure that the mesh doesn't change in that region. So that's also one way to use it. There's also a lot of additional tools within the variable mesh tool. There's a way to make sure that the mesh aligns with specific parts of the geometry so that the grid is exactly the size of your geometry. This is useful for antennas simulation as well, and making sure that the grid is lined up well, and you represent with the highest fidelity possible the size of your geometry in your antenna.
Great. Moving on to the next question. From John, is the discharge propagation speed considered when executing these models or as a part of the simulation flow for checking to make sure that they are representative?
Yes, so the propagation speed is going to be due to the fields, is going to be due to the drift velocities of the particles. All this is captured through the reaction solver and all the reaction and inelastic collisions that we're modeling inside the system. So the discharge propagation speed is something that is validated through the proper modeling of the drift velocities and the field calculation.
Great. Moving on from the next question, also from John, he said, with the 2D simulations, can a particle source be implemented for an internal ESD type simulation, or are only voltage/current sources supported?
Yeah, you can, even with 2D simulations, you can use G4, G4 for charging the dielectric. I think that's what the question is there.
And he also followed up with, can you use a particle source in 2D simulation?
Yeah, I think that's, yeah, I agree. That's, yes, the answer is yes. I actually haven't tried it, but I don't think there is any reason why you can't do it. So it's not actually truly 2D, those simulations. What we're doing is we are just creating a slice of the geometry, and then we're extruding it for 1 millimeter or 0.1 millimeter, depending on what the mesh size is, so that you only have 2 or 3 mesh elements along the thickness. So effectively, it's the whole numerical method is still 3D, but we are just cutting the geometry and making it 2D, so that we can reduce the mesh count significantly.
Great. And then the final question, could you contrast again when discharge should be modeled in EMA 3D and in charge?
Yeah, so at the end of the day, all discharges are modeled in charge plus. In terms of which electromagnetic solver is used, it's going to be either the finite difference time domain or the finite element method for the electromagnetic solver. The FDTD is in the EMA 3D tab, and that is going to be using the nonlinear air chemistry model. So it's very focused on modeling air discharges. If you want to model anything else than an air discharge, then you have to go to the time domain FEM solver in the charge
Great.
tab. Yep.
Thank you so much for answering those questions, Kevin. And I think that was the last one, so we'll just give it another minute or so if anyone has any last minute questions, and then we'll end the session. Okay, great. It seems like no one else has any questions. Thank you, everyone. It is time to conclude this session. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. And if you have any questions about a particular section of interest to you, please feel free to reach out either through the EMA 3D website or email. Next up, we're looking forward to the upcoming space workshop, Space Environment Simulation Testing and Measurement, another no-cost virtual event including several training workshops and technical discussions, which will begin tomorrow, June 24th at 11 a.m. Eastern Time. Thank you all for your time and your attention, and have a great rest of your day.